the previous lecture, we began to discuss commutative Banach algebras, and we introduced the main notions of this theory, namely the maximal spectrum and the Gelfand transform. So let's now briefly recall the construction. We start with a commutative unital Banach algebra, A, and we consider the following two sets. First of all, we denote by max of A the set of all maximal ideals of our algebra. And we also consider A hat, which is the character space, which consists of all non-zero characters, that is, of all non-zero homomorphisms from A to the complex numbers. So we have an obvious map from here to here, which takes each character to its kernel. So this construction makes sense for arbitrary commutative unital algebras. In the general case, this map is easily seen to be injective. And our first important observation was that if A is a Banach algebra, a commutative unital Banach algebra, then all maximal ideals of A are closed, and this map is a bijection. So we often identify the maximal spectrum and the character space of our algebra. And then we introduce a topology on this space, on a set. Namely, we recall that all characters are continuous. So A hat is contained in the dual space, A star. We equip A star with the weak star topology. And we define the Gelfand topology on the spectrum to be the restriction of the weak star topology from the dual space. We proved that the Gelfand spectrum is compact and Hausdorff with respect to the Gelfand topology. This follows from the Banach-Aloglu theorem. And finally, we introduced the Gelfand transform, gamma A, which is a homomorphism from A to the algebra of continuous functions on the maximal spectrum. And this homomorphism is defined as follows. It takes each element in our algebra to a function A hat, which is called the Gelfand transform of our element little a, and A hat is given by the following formula. So this is our main construction and the most fundamental construction in the theory of commutative Banach algebras. This homomorphism has a number of remarkable properties. At this point, I'll not recall all of them. For example, let's recall that the kernel of the Gelfand transform is the intersection of all maximal ideals. The intersection of all maximal ideals has a special name. It is the so-called Jacobson radical of our algebra. And the algebra A is called Jacobson semisimple if the Jacobson radical is 0. So in this case, if it is Jacobson semisimple, then the Gelfand transform is injective. I don't claim that it is isometric, and I don't claim that it is topologically injective. In general, this is not the case. But nevertheless, this map is often injective. Okay, let's now look at some concrete examples of the Gelfand transform. More exactly, we will discuss now the Gelfand transform for some subalgebras in the algebra of continuous functions on the compact Hausdorff topological space. The Gelfand transform for some subalgebras of C of x. Roughly, our main result will be that if A is a subalgebra of C of x, satisfying some reasonable conditions, then very often its Gelfand transform, first of all, its spectrum can be identified with x, and the Gelfand transform becomes just the inclusion map of our algebra into C of x. So we suppose that X is a compact Hausdorff topological space. And we introduce some notation. So for each point in our space, we consider the evaluation character, epsilon x, on the algebra C of x, which takes each function f to f of x. So clearly this is a character of C of x. And the kernel of this character will be denoted by mx. This is the maximal ideal in C of x, which consists of all functions which vanish at x. We have the following lemma. Suppose that we have an ideal, a proper ideal I, in C of x. I claim that every ideal is contained in mx for suitable x. This result is a kind of an analog of the weak Neustadt Satz for algebras of continuous functions. But of course, it's much easier than the classical Neustadt Satz. So we suppose that this is not the case. Suppose that there is no such x. Or in other words, we suppose that for each x in our space, for each for each x in our space, there is a function in our ideal, fx, such that this function doesn't vanish at x. Now our fx is continuous, so this condition implies that it is non-zero in a suitable neighborhood of x. There is a neighborhood ux of x such that fx doesn't vanish on this neighborhood. Now we use the compactness assumption. Since x is compact, it follows that x can be covered by finitely many neighborhoods of this form. And now we introduce the following function. Let f denote the following sum from 1 to n. Equivalently, we can write this function in the following way. fxi complex conjugate fxi. So clearly this function sits in our ideal I, because each fxi is in the ideal, and so since I is an ideal, the whole sum will be in the same ideal. So this function sits in I, but since each summoned is strictly positive on the respective neighborhood, we conclude that this function f is strictly positive everywhere. In particular, it is non-vanishing, and so it is an invertible element of C of x. F is invertible. But a proper ideal cannot contain an invertible element. So this implies that I is not proper ideal, that is, I is the whole algebra, and this is a contradiction. And this completes the proof. So we see that each ideal is contained in mx for suitable x. As a corollary, we see that if we look at the following map, let's denote it by epsilon, from x to the maximal spectrum of the algebra C of x. So epsilon takes each point x to the respective maximal ideal mx. So this map is bijective. Or equivalently, we can interpret this map as a map from x to the character space of C of x, which is identified with the maximal spectrum. And after this identification, this map takes each point, a little x, to the respective evaluation character. So this is a bijection. Why is it a bijection? Well, formally, our previous lemma implies that this map is surjective. So each maximal ideal is contained in Mx, but this implies that it is exactly Mx by maximality. So this map is surjective. And the injectivity follows from the standard result of general topology, that continuous functions separate the points. If you have two different points, then there is a function, there is a continuous function whose values at these points are different. Okay. We will see soon that, in fact, this map is not only a bijection, but in fact it is a homeomorphism. And not only for C of x, but also for some subalgebras of C of x. Я, честно говоря, не знаю, можно ли его отключать. Наоборот, включать. Бывает так, что-нибудь включишь, а потом на записи не видно. Ну, можно, конечно, попробовать. Я даже не знаю, где это делается, честно говоря. А не видно, что ли, да?
Ну, не знаю, и нет.
Понятно. Ну,
так, просто темно.
Я просто не знаю, где это делается. Вот тут. Ну, нет, тут просто гнезда какие-то. Может быть, там вот. Посмотрите, ладно, я, честно говоря, здесь как никогда этим не занимался, не ориентируюсь. Оп, нет, это не то. Вот сейчас где-то, вот на минуточку вот зажглась на секунду. Ну вот, которая не горела. Или я что-то... Так и было, да? Okay, let's now introduce some notation. Suppose that we have two compact Hausdorff spaces x and y, compact Hausdorff topological spaces, and a continuous map f from x to y. And observe that f induces an algebra homomorphism, which will be denoted by f dot, which acts from C of y to C of x. And f dot acts by the following simple formula. So here are some properties of this induced map. First of all, it's clear that f dot is a unital algebra homomorphism. And moreover, it is bounded, and its norm is 1. This is clear because if we take the supremum of this expression over over x, and then this is less than or equal to the supremum of g over y. And so the norm of f dot is less than or equal to 1. But since it is unital, it takes the identity to the identity. Its norm is exactly 1. Property 2, almost trivial. If we take the identity map of our space X, then the induced homomorphism is also the identity homomorphism of the algebra C of X. And finally, if we have two continuous maps, f from X to Y and g from Y to Z, then the homomorphism induced by their composition, gf dot, is the composition of f dot and g dot. So these properties are immediate from the definition of f dot, and actually they mean that what we've just considered is a contravariant functor from the category of compact Hausdorff spaces to the category of commutative unital Banach algebras. We'll discuss this a bit later, but at this point, let's only observe that the above properties 1, 2, and 3, imply that if f between x and y is a homeomorphism, if f is a homeomorphism, then the induced homomorphism f dot is an isometric isomorphism. An isometric isomorphism. Well, indeed, it will be an isomorphism by properties 2 and 3, namely if f is a homeomorphism and g is the inverse of f, then g dot will be the inverse of f dot. So f dot will be an algebra isomorphism, and it will be actually an isometric isomorphism because the norm of f dot is 1, and the norm of the inverse map g dot is also 1. And if we have an operator, an invertible operator between norm spaces, whose norm is 1, and the norm of the inverse operator is also 1, then this operator is an isometric isomorphism. Okay, now we have the following theorem. As before, we suppose that X is a compact Hausdorff topological space. And suppose that A is a subalgebra in C of X, which contains the identity of C of X. That is, the function which is identically 1 sits in A. And let's also suppose that A satisfies the following conditions. First of all, we suppose that A is a Banach algebra. A is a Banach algebra with respect to a norm which dominates the supremum norm. So this norm can be strictly stronger than the supremum norm. And in particular, A is not necessarily closed in C of X. It is a Banach algebra, but not with respect to the supremum norm, but it is the Banach algebra. It's a Banach algebra with respect to possibly stronger norm than the supremum norm. So a typical example to keep in mind is the algebra of continuously differentiable functions on a closed interval of the real line. The second assumption is that A separates the points. A separates the points of X. And finally, we assume that each character of A is the evaluation character. So for each character of A, there is a point in our space such that chi is the evaluation at X. So if A satisfies these conditions, then the map from X to the character space, which takes each point X to the character epsilon X, is a homeomorphism. And moreover, we have the following commutative diagram. The following diagram commutes. So let's draw a picture. This is A. This is C of X. So A is contained in C of X. This is the inclusion map. We also have the Gelfand transform of A, which takes A to the algebra of continuous functions on the maximal spectrum. This is the Gelfand transform. And also we have an isometric isomorphism here, epsilon dot. So epsilon dot is the isomorphism induced by this map epsilon. So I claim that this diagram commutes. So in other words, roughly this means that if we identify X with the maximal spectrum by means of this bijection, by means of this homeomorphism, then the Gelfand transform, in some sense, becomes just the inclusion map of A into C of X. Okay, so to prove this result, first of all, let's observe that conditions 2 and 3 really imply that epsilon is a bijection. Epsilon is a bijection. Now, the natural question is, why is it continuous? In fact, if we want to show that it is a homeomorphism, it's enough to prove the continuity, because we know that a continuous bijection between compact spaces, compact Hausdorff spaces, is a homeomorphism. So why is it continuous? Here's a simple lemma incorporated into the proof. A simple lemma about the weak star topology. So suppose that X is an arbitrary topological space, and E is a topological vector space. And suppose that we have a map phi from X to the dual of E. And the dual of E is equipped with the weak star topology. So I claim that phi is continuous if and only if for each vector V in our space, the function phi V from X to the complex numbers, which is basically the composition of phi with the valuation at V, is continuous. The proof is a simple exercise for you. This is actually an exercise in general topology. So everything is almost immediate from the definition of the weak star topology on E star. Okay, let's now come back to the proof of our theorem. By lemma, epsilon is continuous if and only if for each element. So epsilon takes X to a hat, and a hat is a subset in the weak star dual. A star. So epsilon is continuous if and only if for each A in our algebra, the map which takes x to epsilon of x of A is continuous. Now what is epsilon of x applied to A? This is just A of x, because epsilon of x is the evaluation map. So this is A of x, and A is continuous by assumption. A is a subalgebra in C of x. So A is continuous, and so our lemma implies that epsilon is continuous. And since epsilon is a continuous bijection between compact Hausdorff spaces, it is a homeomorphism. By compactness. Okay, so finally we have to show that the diagram commutes. Well, just one line. Let's do it here. So we have to show that gamma composed with epsilon dot is the inclusion map. Okay, epsilon dot gamma. So we apply this composition to little a and evaluate this at point x. So what is this? So first of all, we apply gamma to A, then apply epsilon dot and evaluate at x. So by the definition of epsilon dot, this is gamma of A at epsilon x. Okay, now we recall the definition of gamma. And we see that this is nothing but epsilon x evaluated at A, which is just A of x. And that's it. So it shows that our composition is the inclusion map. So this completes the proof. This theorem is very useful. It applies to many concrete commutative Banach algebras. So many examples will be in our next and final exercise sheet. As a corollary, we get the following result. So let A be just C of x, where x, as before, x is a compact Hausdorff space. Then the Gelfand transform, gamma A, is an isometric isomorphism. And moreover, the inverse map is nothing but epsilon dot. This is a special case of our previous theorem, because in this case, this error is just the equality. And since epsilon dot is an isometric isomorphism, this diagram implies that gamma is the inverse of epsilon dot. And since epsilon dot is isometric, so is gamma A. So gamma A is isometric because epsilon dot is isometric. Okay, our next goal will be to discuss C-star algebras and to prove an important result about them, namely the so-called first Gelfand-Nymark theorem. C-star algebras and the Gelfand-Nymark theorem. C-star algebras were introduced by Gelfand and Nymark in 1943, and they form one of the most important, or probably maybe the most important, class of Banach algebras, which has numerous relations to other fields of mathematics and many interesting applications. So we start with some algebraic definitions. Suppose that A is an algebra, just an algebra over the complex numbers. The involution on A, an involution, there can be many involutions, of course, an involution on A is a map from A to itself, which takes each element in our algebra to an element denoted by A star, such that this map satisfies the following conditions. First of all, it is an involution in the purely set-theoretic sense. That is, if we apply it twice, then we get the identity map. A double star is A. Second, this map is antilinear. So if we apply it to any linear combination, then we get the linear combination with complex conjugate coefficients. And finally, we require that this map is a ring anti-homomorphism. Anti-homomorphism means that AB star equals B star A star for each A and B. An algebra with a fixed involution is called a star algebra. So formally, a pair consisting of an algebra A and an involution on A is called a star algebra. Okay, so this definition is purely algebraic. Now we come back to functional analysis. So by definition, Banach star algebra is Banach algebra A equipped with an involution such that the involution is isometric. The norm of A star equals the norm of A. And finally, we give our main definition. C star algebra is a Banach star algebra A such that A satisfies the following axiom. The norm of A star A equals the norm of A squared for each element in our algebra. So this axiom is sometimes called the C star axiom or the C star identity. And it is extremely important. If we compare the theory of Banach star algebras with the theory of C star algebras, we see that actually these theories are very different. So this extra axiom leads to a very rich and powerful structure of C-star algebras. Okay, so these are our objects. Let's now introduce suitable morphisms between them. So if you have two star algebras A and B, and you have an algebra homomorphism, phi from A to B, then we say that phi is a star homomorphism. The star homomorphism if it preserves the involution in the following sense. And one more definition. If A is a star algebra and B is a subalgebra of A, then we say that B is a star subalgebra. B is a star subalgebra if it is stable under involution for each element in B. B star is also in the same subalgebra. It's clear from this definition that a star subalgebra is also a star algebra with respect to the same involution. And a closed star subalgebra of a Banach star algebra is also a Banach star algebra. And in particular, a closed star subalgebra of a C-star algebra is also a C-star algebra. Okay, let's now look at some examples. First of all, observe that the field of complex numbers is a C-star algebra. The involution is just the complex conjugation. And obviously, all axioms are satisfied. Here is a more interesting example. Let's look at the algebra of bounded complex valued functions, little L infinity of x. The algebra of bounded functions on x. So we know that it's a Banach algebra with respect to the supremum norm, but it is easily seen that this is a C-star algebra for any set x. Namely, the involution on this algebra is just the pointwise complex conjugation. Again, all axioms are easily verified. So it's a C-star algebra. Okay, let's now suppose that X is not just a set, but is a topological space. And let's look at the algebra CB of X of continuous bounded functions. Continuous bounded functions on X. It's a standard result that this is a closed subalgebra in little infinity of X. In other words, the uniform limit of continuous functions is continuous. And moreover, it is a star subalgebra. So it is a closed star subalgebra of the algebra of bounded functions. And so it is a C-star algebra. An important special case is the case where X is compact. So in particular, if X is compact, then C of X, the algebra of continuous functions, is a C-star algebra. because if x is compact, then all continuous functions are bounded. In this case, c of x is equal to cb of x. But of course, if x is not compact, then c of x is not a Banach algebra. There is no natural norm on c of x. We know that it's a locally convex space, and moreover, c of x will be a locally convex algebra, but it is not a Banach algebra unless x is compact. One more example of the same sort. Suppose that we have a measure space x mu, a measure space. Then it's easily seen that the algebra bigger than infinity of x mu, which consists of equivalence classes of essentially bounded measurable functions. So we know that it's a Banach algebra, but in fact, it's easily seen to be a C-star algebra. It's a C-star algebra with respect to the same involution. The involution is the pointwise complex conjugation. The following example is probably the most important for us, and in fact, it serves as a motivation to introduce C-star algebras. Namely, if H is a Hilbert space, then the algebra B of H, of bounded linear operators on H, is a C-star algebra. And we proved that some time ago when we discussed the notion of the Hilbert adjoint operator. So when we discussed Hilbert adjoint operators, we proved that the operation of taking the adjoint operator satisfies all these conditions. It is an involution, it is isometric, and it satisfies the C-star axiom. So B of H is one of the most important examples of a C-star algebra. One more example, which is also important, and which provides an important example of a non-unital C-star algebra. Namely, again, if H is a Hilbert space, then K of H, the set of compact operators on H, is a closed star ideal of B of H. We proved this some time ago, that it's an ideal. It is closed, and it's a star ideal. So the adjoint of a compact operator is also compact. In particular, it's a closed star subalgebra, and so it is a C-star algebra. In general, it is non-unital. It is non-unital unless X is finite dimensional. Unless H is finite dimensional. Let's now look at a non-example, or more exactly at an example of a Banach star algebra, which is not a C-star algebra. Let's look at the algebra of n times continuously differentiable functions on the interval AB, Cn of AB. So let's recall a standard fact that it is a Banach algebra. This is a Banach algebra with respect to the following canonical norm. The norm of f is the following finite sum. So for each k from 0 to n, we take the supremum norm of the kth derivative and divide over k factorial. So this is the standard norm on this algebra, and it's a Banach algebra with respect to this norm. And also it's easy to see that it is a Banach star algebra. A Banach star algebra with respect to the same involution as before. So the involution is the pointwise complex conjugation. similarly to the examples on that part of the blackboard. But it is not a C-star algebra. This is not a C-star algebra unless n is 0. If n is 0, then this is the algebra of continuous functions, which is a C-star algebra. But if n is at least 1, then this is not a C-star algebra. Okay, let's now introduce some terminology, which we already introduced in the case where our algebra is B of H, the algebra of bounded operators on a Hilbert space. So suppose that A is a star algebra. First, we say that an element little a in our algebra is self-adjoint or Hermitian if A equals A star. More generally, we say that little a is normal. A is normal if A commutes with A star. And if our algebra is unital, if A is unital, then we say that an element little u of our algebra is unitary. Is unitary if it is invertible. And u inverse equals u star. Here's a simple observation. Let's observe, first of all, that each self-adjoint element and each unitary element is normal. So each self-adjoint element is normal. And each unitary element is also normal. So probably this is one of the main reasons to introduce normal elements. Normal elements are important, in particular because they generalize both self-adjoint elements and unitary elements. And one more simple observation is that for each element little a of our algebra, the element A star A is always self-adjoint. This is clear from the axioms of the involution, but this is quite useful. The set of all self-adjoint elements will be denoted by A S A. Actually, this is not just a set. This is a real vector subspace in A. It's not a complex vector subspace because when we multiply self-adjoint element by, say, I, or any non-real complex number, the result will not be self-adjoint. But anyway, this is a real vector subspace of A. Let's look at some concrete examples. For example, suppose that A is the algebra of all functions on an arbitrary set X, or the algebra of bounded functions on a set X. Or we can take the algebra of CB of X, of continuous bounded functions on a topological space. So we observe that a function f in our algebra is self-adjoint, even only if it is a real. F of x is real for all x. And it is unitary even only if the absolute value of f of x is 1 for each x. And another example, and an exercise at the same time. Example exercise. Let's now take the algebra of bounded operators on the Hilbert space. I claim that self-adjoint operators and unitary operators can be characterized in terms of the inner product. Namely, an operator T is self-adjoint even only if the following function, which is called the quadratic form of our operator, is a real for each vector in our space. And second, an operator U on H is unitary in the sense of our previous definition, even only if it is unitary in the usual geometric sense, that is, even only if U is bijective and preserves the inner product. This is a simple but useful exercise. So morally, self-adjoint elements should be interpreted as analogs of real numbers. So if we interpret elements of our algebra as analogs of numbers, then self-adjoint elements are analogs of real numbers. And unitary elements are analogs of those numbers which sit on the unit circle. And the following proposition emphasizes this analogy. So for each element A in our algebra, there is a unique pair AB or BC of self-adjoint elements such that A equals B plus IC. So in some sense, B is the real part and C is the imaginary part. The proof is very easy. B and C are given by the following explicit formulas. So clearly they are self-adjoint, and A equals B plus IC. And the uniqueness is a simple exercise. So we just write this, then take the star of this, and deduce this explicit formula for B and C. This is very easy. We now have the following important theorem about normal elements. Theorem 1. Suppose that A is a unital C-star algebra. A unital C-star algebra. And little a is a normal element. I claim that the norm of A is equal to the spectral radius. The norm of a normal element is equal to the spectral radius. Okay, let's recall that some time ago we proved this result for the algebra of bounded operators on the Hilbert space. So if we try to recall the proof, we will easily see that the same proof works for an arbitrary unital C-star algebra, for an arbitrary unital C-star algebra. So the proof for B of H actually involved only the axioms of a C-star algebra. And so it works for an arbitrary C-star algebra. Let's now look at some corollaries of this result. Corollary 1. If A is a unital C-star algebra, then for each element in A, we have the following equality. Then the norm of A is the square root of the spectral radius of A star A. This is a combination of theorem 1 with the C-star axiom. So the norm of A star A is self-adjoint. So the norm of A star A equals the spectral radius, but by the C-star axiom, the norm of A star A is the norm of A squared. And so we get this formula. Why is it useful? Well, let's observe that the right-hand side of this formula is purely algebraic in the sense that it is defined entirely in terms of the algebraic structure on A. So it doesn't involve the norm. So this formula shows that we can reconstruct the norm on A from its algebraic structure. In other words, we have the following corollary. Corollary 2. If A is a unital star algebra, then there is at most one norm on A that makes A into a C-star algebra. This is immediate from this formula. I don't claim that such a norm always exists, but if it does exist, then it should be given by this formula. Equivalently, this means the following. Equivalently, every star isomorphism between unital C-star algebras, every unital star isomorphism between unital C-star algebras is isometric. We can generalize this result as follows, corollary 3. Suppose now that A is a unital Banach star algebra, and B is a unital C star algebra. And suppose that phi is a unital star homomorphism from A to B. I claim that phi is automatically continuous. Phi is continuous. And the norm of phi is less than or equal to 1. And actually, it is exactly 1 if our algebras are non-zero, because it takes the identity to the identity. Well, why is it so? First of all, we observe that if we take a self-adjoint element, if little a is a self-adjoint element of A, then of course phi of A is also self-adjoint, because phi is a star homomorphism, so it takes self-adjoint elements to self-adjoint elements. And so the norm of phi of A is equal to the spectral radius of phi of A by the previous theorem, by theorem 1. Now phi is a unital homomorphism, and we know that a unital homomorphism doesn't increase the spectrum. So the spectrum of phi of A is contained in the spectrum of A. And therefore, the spectral radius of phi of A is less than or equal to the spectral radius of A. This is true for each unital homomorphism. But the spectral radius of A, so little a is an element of Banach star algebra, so the spectral radius is less than or equal to the norm. And we get this equality. The norm of phi of A is less than or equal to the norm of A. So this is true for each self-adjoint element. If we now take an arbitrary element, we can apply the same to the element A star A, which is self-adjoint. So the C star axiom gives us the following equality. Now phi is a star homomorphism, so we see that this is the norm of the image of A star A. Now A star A is self-adjoint. This is self-adjoint element. And so by the previous line, this is less than or equal to the norm of A star A. And the norm of A star A by the submultiplicativity and by the axioms of a Banach star algebra, this is less than or equal to the norm of A squared. And that's it. So we see that the same inequality, the norm of phi of A is less than or equal to the norm of A, holds for an arbitrary element of our algebra A. Okay. Our next result, which is also quite important. This one. Well, if we have, this is a pure algebraic result. If we have two unital algebras, A and B, two unital algebras, and a unital homomorphism phi from A to B, a unital homomorphism, then first of all, phi takes invertibles to invertibles. And this implies that the spectrum of phi of A is contained in the spectrum of A. Because if little a, if phi of A is not invertible, then this inclusion implies that little a is also not invertible. So we get this inclusion, and when we take the supremum, we see that the spectral radius of phi of A is less than or equal to the spectral radius of A. So actually, this is a pure algebraic result. And here we apply it to the element phi of A, where A is self-adjoint. Okay, now theorem 2, another fundamental result about C-star algebras. Suppose that A is a unital C-star algebra, and little a is a self-adjoint element of A. I claim that the spectrum of A is real. The spectrum of a self-adjoint element is real. So here the situation is the same as the situation with theorem 1. Some time ago, we have already proved this result for the algebra of bounded operators on the Hilbert space. And again, I deliberately chosen the proof which works for an arbitrary unital C-star algebra. So now we can just refer to the proof for B of H. Okay, now let's look at some corollaries. Corollary 1. Suppose that A is a unital C-star algebra. And suppose that chi is a character of A. I claim that chi is a star character. Each character of a C-star algebra is a star character. That is, it preserves the involution. Again, we start with the case where little a is a self-adjoint element. If little a is a self-adjoint element, then, well, the spectrum of chi of A is contained in the spectrum of A, which is real by the previous theorem. But this means exactly, well, the spectrum of a complex number consists only of this complex number. So this inclusion means that chi of A is real. So we see that chi takes self-adjoint elements to real numbers. Let's now take an arbitrary element in our algebra. And let's write it in the form B plus IC, where B and C are self-adjoint elements. So by the previous line, we see that chi of B and chi of C are real numbers. Now, we simply calculate chi of A star. So what is A star? A star is B minus IC. So this is chi of B minus I chi of C. But since these numbers are real, it follows that this can be written as the complex conjugate to chi of B plus I chi of C. But this is nothing but chi of A. And that's it. So we see that chi preserves the involution. That is, it's a star character. Another important corollary of theorem 2 is the spectral invariance of C-star subalgebras. Let's recall some general definitions, or maybe not before definitions. Let's recall the following general situation. So suppose that A is a unital algebra, and B is a subalgebra of A, which contains the identity of A. So if we apply now this general observation to the inclusion map of B into A, we see that we have the following inclusion, which is more or less trivial. Each element which is invertible in B is invertible in A. And we have the following inclusion for the spectrum of any element in our subalgebra calculated with respect to A is contained in the spectrum of the same element calculated with respect to B, to the smaller subalgebra. So we now give the following definition. We say that B is spectrally invariant. B is spectrally invariant in A if these sets are the same. In other words, if each element in the subalgebra B, which is invertible in the bigger algebra, is invertible already in B. Or equivalently, this means that for each element in B, the spectra are the same. This equivalence is a little exercise for you. We discussed this in the previous term, but anyway, it is very easy. So these two conditions are equivalent. And in this case, we say that B is spectrally invariant in A. And now we have the following corollary of theorem 2, corollary 2. Suppose that A is a unital C-star algebra, and B is a closed star subalgebra of A. Closed star subalgebra, which contains the identity of A. Then B is spectrally invariant in A. So we have to show, so we will prove this, this equality. So we'll show that each element in B, which is invertible in A, will be invertible in B. So suppose that little b is an element in B, which is invertible in A. We take the element B star B. This is a self-adjoint element, and it is still invertible in A. So the product of, if B is invertible, then clearly B star is also invertible, and the product of two invertibles is invertible. Well, it is self-adjoint. So by theorem 2, its spectrum is real. Its spectrum is real. And so for each non-zero real number t, the element B star B plus I t1 is invertible in B. So we now take the inverse element. And observe that this goes to B star B inverse as t goes to 0 by the continuity of the inversion map. Okay, but now, since this element is invertible not only in A but also in B, we see that this element sits in B. And B is closed. Since B is closed, we conclude that B star B inverse sits in B. Okay, we now write the following obvious equality. So this product is 1. If we now put the brackets in this way, we conclude that B is left invertible. Little b is left invertible in the algebra B. This is not exactly that we wanted to prove. We wanted to show that B is invertible. But we can now repeat the same argument and apply it to the element BB star. So now the same argument applied to BB star. shows that B is right invertible. In the subalgebra B. And it's a simple algebraic result that an element which is left invertible and right invertible is invertible. And this completes the proof. Oh, I see that it's time to finish. Okay, so actually we are now we're now in a position to prove the Gelfand-Naimark theorem, which is quite easy, but it is also very important. So let's do it at the beginning of the next lecture. So actually I can state the result even now. The result is that if we take a unital, a commutative unital C-star algebra A, then the Gelfand transform of A will be an isometric star isomorphism between A and the algebra of continuous functions on the maximal spectrum. This is very useful, and this result has many important corollaries. From our point of view, I mean from the point of view of applications to operator theory, we will see that this result will enable us to construct the so-called continuous functional calculus for each normal operator on a Hilbert space. And this is the continuous functional calculus is the key ingredient in proving the spectral theorem for normal operators. But in fact, there are many other different applications of the Gelfand-Naimark theorem. In particular, it leads us directly to non-commutative geometry and to K-theory of operator algebras. So I'll tell you some more words about these applications at the beginning of the next lecture.